Welcome back to the Deep Dive, where we take your stack of sources, articles, research notes, and we plunge into the material to pull out the essential knowledge and insights you need. Today, we are undertaking a monumental task. We're mapping the literal abyss.
Not just mapping it. We're trying to fundamentally rethink what that abyss means for the planet right beneath our feet. Our focus today is on Marie Tharp, an American geologist and cartographer whose work didn't just chart the bottom of the sea.
No, it did so much more.
It provided the visual, the physical proof that forced the entire field of Earth science to embrace continental drift and, well, eventually, the theory of plate tectonics.
Okay, let's unpack this and set our mission for this deep dive. We're looking at a really powerful narrative here. It's Tharp's life, her difficult path in a field that, let's be honest, actively excluded her.
Absolutely.
And the outcome is almost unbelievable. A cartographer who was often barred from even stepping onto a research ship used meticulous, grueling data plotting to reveal a massive hidden feature that completely changed our model of the planet.
It's a classic story.
It really is. It's a story of persistence and of data just overcoming generations of scientific dogma.
It truly is a remarkable story, especially when you consider the context. I mean, to really grasp the significance of her work, we have to recognize the sheer scale of the geographical ignorance.
The ignorance surrounding the ocean floors.
Yes, before the 1950s. Well, we had some general ideas. The vast majority of the seabed was a complete topographical mystery, a blank slate.
Right.
So Tharp's discovery, which focused on the mid-Atlantic ridge, it wasn't just a curiosity. It was the critical, undeniable physical evidence. It was the smoking gun.
The smoking gun that the more abstract theories, like plate tectonics, had lacked for decades.
Precisely. Without our map, that theory might have just remained on the fringes for much, much longer.
Let's dive right into the source material then. We should probably start at the beginning of this truly unconventional path. Marie Tharp, born July 30, 1920, in Ypsilanti, Michigan. The source material immediately points to the origin of her map-making roots, and it came directly through her father.
That foundation was built by William Edgar Tharp. He worked as a soil surveyor for the United States Department of Agriculture.
And soil surveying, that's not just digging in the dirt. We have to be clear about what that job entailed back then.
Oh, not at all. It is, in essence, incredibly detailed map-making, but for agricultural purposes. It requires immense precision in grading, classification, and mapping all the features of the land.
It's rigorous cartography.
Absolutely. And crucially, Marie often accompanied him on his fieldwork.
So this wasn't just a casual hobby or hearing about it at the dinner table.
No, this was a direct, hands-on introduction to map-making and survey work from a very, very young age. She was basically an apprentice to a professional cartographer.
But here we hit that early 20th century paradox, that contradiction the sources point out.
Yeah. Despite being exposed to the rigorous fieldwork and the technical skill it required, she initially saw the physical act of surveying and exploration as explicitly men's work.
So she understood the technique, but she couldn't see herself in that role.
Exactly. The sources make it really clear she didn't internalize it as a viable professional path for herself. It just shows you how deeply entrenched those societal limitations were, even when the talent and the interest were clearly there.
That initial acceptance of limitation, it makes her later career, where she just redefined the limits of her field, so much more powerful.
Her childhood, though, was highly unusual, and it was because of her father's job.
Right, he was nomadic.
Very. Due to the nature of a USDA soil surveyor's job, moving to map different areas of the country, the family moved constantly until William Tharp retired in 1931.
And we are talking about attending over 17 public schools.
17. Across states like Alabama, Iowa, Michigan, Indiana.
I can't even imagine the challenge of that. Attending 17 schools means every single year you are the new kid, you're starting over socially, trying to catch up with different curricula. It sounds like a childhood just defined by impermanence.
It really does. And it highlights a powerful theme in her life. Her environment was constantly shifting, but her academic pursuit, her curiosity, that became her source of stability.
The sources point to one year in particular.
Yes, one full school year in Florence, Alabama, seems to have been particularly influential. She attended a class called Current Science.
Current Science.
Yeah, and in it she learned about contemporary research and living scientists. This focus on current active discovery seems to have really cemented her curiosity and gave her an anchor in that constantly moving world.
So she graduates high school in Bellefontaine, Ohio, where the family finally put down roots. But even then, she didn't just jump straight into a science career.
No, not at all. She spent a couple of years working on the family farm before she entered Ohio University in 1939. And famously, she changed her major constantly.
She was exploring.
She was definitely exploring.
Yeah.
She eventually graduated in 1943 with degrees in, get this, English and music.
English and music, plus 4 minors, none of which scream future oceanographic revolutionary.
Not even a little bit. The fact that she was so intellectually curious across such diverse fields is telling. But the real career pivot, the thing that pushed her towards science, was imposed by global circumstances.
That pivot, of course, was World War II. It created this massive, temporary professional vacuum in a lot of specialized technical fields.
Precisely. Before the war, professions like petroleum geology were almost entirely restricted to men. But once the young men left for military service, American universities scrambled to fill their classrooms.
Right. They had to maintain funding and output, particularly in fields that were crucial to the war effort.
Like geology for finding oil and other strategic resources.
And Tharp seized that exact window of opportunity. The University of Michigan, which had previously barred women from its geology program, suddenly opened its doors.
Tharp enrolled in the petroleum geology program there in Ann Arbor, and she earned her master's degree in 1944. And it's really hard to overstate how significant this was.
Let's put it in context.
Our source material notes that at the time, fewer than 4% of all earth science doctorates were obtained by women. This wasn't just a change of major for her. It was breaking a major institutional barrier, even if that barrier was only temporarily lowered because of the war.
It's a perfect example of a societal crisis creating an unexpected and, frankly, a necessary opportunity. However, those barriers immediately reformed once she entered the professional world.
Oh, they snapped right back into place. Her first job was as a junior geologist at the Stanland Oil Company in Tulsa, Oklahoma.
And even with a master's degree in the field.
She had the credentials, but the rules remained rigid. The Stanland Oil Company absolutely did not permit women to attend or conduct fieldwork, period. Her role was restricted entirely to coordinating maps and processing data that her male colleagues collected out in the field.
So she was more than qualified to do the primary research, but she was relegated to being this high-level organizer and desk jockey.
Yes. But this constraint, this limitation, it actually led to her next brilliant move. Rather than letting it define her career, she decided to expand her toolbox.
How so?
She concurrently enrolled in the University of Tulsa's mathematics program and obtained a second Bachelor of Science degree.
That's the real strategic genius right there. If they wouldn't let her do geology in the field, she decided she was going to become completely unbeatable at the geometry, the cartography, and the pure data analysis back in the office.
And that rigorous training in mathematics proved absolutely essential for what was to come. Bathymetry, the measurement of ocean depth, is inherently mathematical.
It's all numbers.
All numbers. It involves complex conversions, corrections for water temperature and salinity, triangulation. By mastering the quantitative side, she built the analytical engine that allowed her to synthesize these massive, messy data sets, and it prepared her for the revolutionary work to come.
Okay, so after 4 years in Tulsa, Tharp moves to New York City in 1948. She's looking for new professional territory, and this eventually leads her to Columbia University.
That's right. She found drafting work at the newly established Lamont Geological Observatory, or LGO. This was a place founded by the highly ambitious and, frankly, very competitive Maurice Ewing.
And LGO was a powerhouse, right?
Oh, yeah. It was a powerhouse of cutting-edge, government-funded deep-sea research. It was where all the action was, but it was also a fiercely masculine environment.
And this leads to that fascinating biographical detail from the sources. When she interviewed for the drafting job, she strategically chose not to mention her master's degree in petroleum geology.
It speaks volumes about the professional climate at the time, doesn't it?
It really does.
A master's degree might have immediately labeled her as overqualified for what they saw as technical support, or worse, she might have been perceived as a direct challenge to the male scientists.
So she played it smart.
She likely understood that to get her foot in the door and start working with the real data, which is what she wanted, she needed to present herself as a skilled technical professional, not as a potential principal investigator.
And it worked. She became one of the very first women working at LGO.
It was there that she met the geologist Bruce Heezen, who was a graduate student at the time, and he quickly recognized her unique skill set, which led to a professional partnership that would last for 30 years.
Their initial projects were pretty pragmatic, very tied to the post-war context.
Very. They were focusing on the Cold War. They used photographic data to map the deep ocean floor to locate things like downed military aircraft from World War II.
And later on, mapping the paths of turbidity currents, which are essentially undersea landslides.
Right. But she eventually started working for Heezen exclusively, funneling all her geological knowledge and her advanced mathematical and drafting skills into one monumental and pretty thankless task.
Plotting the vast, seemingly featureless topography of the ocean floor.
And here we have to re-emphasize the gender divide. It's so central to the story. For the first 18 years of their critical collaboration, Heezen was out on the research ship, the Vema, collecting the raw bathymetric data with echo sounders,
While Tharp was confined to the lab in New York.
meticulously drawing maps from the data he literally mailed back to her.
She was the cartographic genius behind the operation, yet she was literally barred from the place she was mapping. She couldn't verify the instruments, she couldn't observe the conditions.
She couldn't participate in the physical collection of the very data she was analyzing. It's astounding.
And it wasn't until 1968 on the USNS Kane that she finally participated in a data collection cruise, 18 years later.
But that confinement, that restriction, it forced her into a synthetic role that was ultimately her greatest advantage.
How do you mean?
Well, while Heezen was focused on the specific, often messy, day-to-day collection process out at sea, Tharp was forced to look at the macro picture back in the lab. She independently synthesized multiple data streams.
Right. It wasn't just Heezen's data.
No, she was pulling in Heezen soundings, older data from the Woods Hole Oceanographic Institution's ship Atlantis, and even seismographic data from undersea earthquakes.
That cross-referencing process, that synthesis, that's where the real magic happens. But it must have been an absolute nightmare of complexity.
Oh, just imagine the technical challenge. They were using 1950s technology. We're talking single-beam echo sounders.
So the ship sends a single ping straight down.
Straight down. It waits for the echo and measures the depth based on the travel time. But this process was so prone to error.
Why is that?
Sound velocity changes with water temperature, with pressure, with salinity. The early systems had to be calibrated constantly. And even more fundamentally, without modern GPS, navigation was crude.
So you might not even know exactly where the ship is when it takes the measurement.
Exactly. A slight error in the ship's plotted position could mean miles of error on the final map.
And she had to reconcile data taken over a 30-year span by different ships using different calibration methods and often with these just very sparse lines of travel. It's not like they were mowing the lawn out there.
Not at all. So she wasn't just plotting a few lines. She was taking these sporadic, often inconsistent slices of information and interpolating a smooth, logical, three-dimensional topographical map of a surface she had never even seen.
This was the first systematic attempt to map the entire ocean floor.
The very first. And it demanded the precision of a mathematician combined with the spatial intuition of a geologist. She had to believe implicitly in the consistency of the data, even when it seemed contradictory, because she knew the map wouldn't lie if it was plotted correctly.
This sounds like the absolute epitome of forensic science, but applied to geology. Using these tiny fragments of information to reconstruct a massive, complex truth. Okay, let's turn to the core discovery. Before the 1950s, the geology community had been wrestling with the question of the Earth's structure. We knew how to map mountains and valleys on land.
But without any real knowledge of the seafloor, any theory about how the Earth moved was just incomplete speculation.
There's a huge blind spot.
A geological vacuum. And theories of Earth's structure were just stalled. Geologists knew there was a mountain range running down the middle of the Atlantic, the Mid-Atlantic Ridge, or MAR, but they didn't know its true shape or its function.
And mapping it was essential to answering that bigger planetary question of global evolution. Tharp's breakthrough happened around 1952. She was aligning profiles, those cross-sections of depth data, primarily from the Atlantis cruises, and one very early profile from a naval ship, the Stuart.
She generated approximately 6 detailed profiles stretching west to east across the North Atlantic, and she was focusing specifically on the central axis of that known mountain range.
And this required just an immense amount of manual labor, calculating depths, correcting positions, drawing these continuous smooth lines all by hand.
Painstaking work.
Yeah.
And it was in that painstaking repetitive labor that she spotted the anomaly, the aha moment.
So what did she see? What jumped out from the data?
She identified an aligned, continuous, deep V-shaped structure that ran exactly down the center line of the Mid-Atlantic Ridge axis. This wasn't just a valley. It had a very distinct morphology.
A V-shape?
Yes. And she immediately hypothesized that this V-shape was a rift valley, a massive crack where the oceanic surface was actively being pulled apart.
Wait, okay, so why is a V-shaped crack so different from a regular canyon or a valley? Why did that specific shape scream tectonic action to her?
Well, a standard valley, like a river valley, is often formed by erosion or sometimes by folding of the crust. A V-shaped rift running continuously for thousands of miles along the highest point of a mountain range.
The very spine of the mountain
That
range.
suggests a tensile force. It suggests the crust is being stretched and split open. If you see a crack running down the spine of a massive underwater mountain range, it implies a fundamental weakness, a place where new materials rising from below and pushing the sides apart.
This was direct evidence of seafloor spreading.
The first real physical evidence. And that idea, seafloor spreading, was the critical missing piece for the theory of continental drift, which at the time was still considered pseudoscience by many mainstream geologists.
A fringe theory.
Absolutely. Continental drift, originally proposed by Alfred Wegener, suggested continents moved laterally across the globe. But the mechanism, the engine driving that movement, was completely missing.
And Tharp's Rift Valley provided that engine.
It did. Magma rising from the mantle at the rift, creating new crust and pushing the older crust away on either side. It was beautiful. It was elegant.
But the immediate reaction, even from her own partner, Bruce Heezen, was one of profound skepticism, if not, outright rejection.
Heezen was highly uncomfortable with the finding. The discovery of a central rift valley was just too strong a piece of evidence for continental drift, a theory he and much of the geological establishment publicly rejected.
And at the time, Heezen publicly favored a different hypothesis instead.
That's right, the expanding Earth hypothesis.
We need to explain that because it's central to understanding why he was so quick to dismiss her finding. Why would Heezen prefer expanding Earth?
Well, the expanding Earth model essentially posits that the planet is slowly inflating, kind of like a balloon.
Okay.
As the planet expands, the crust stretches and cracks, creating new ocean floor. This model explains why the continents are separating. They're just riding outward on an expanding globe, without requiring a really complicated mechanism like subduction.
And subduction is where old ocean floor has to be destroyed somewhere else, right? Pushed back down into the mantle.
Exactly. Geologists in the 50s had a lot of trouble finding evidence of subduction, so the expanding Earth hypothesis seemed simpler to some. It was a cleaner explanation, even if it had its own massive problems like where all the new mass was coming from.
So Tharp's discovery of a rift actually fit both theories in a way, but the expanding Earth model avoided that messy problem of continent collision and sinking crust.
Correct. And because her finding was so radical, and because it challenged the prevailing static view of the Earth, Heezen defaulted to the easiest possible dismissal he could find.
And this is the moment documented in our sources. The infamous quote.
He famously dismissed Tharp's explanation as girl talk.
That phrase, girl talk, it just perfectly encapsulates the systemic resistance she was up against. It wasn't just a scientific disagreement.
No, it was a rejection based on gender. It was a refusal to believe that someone without the pedigree of fieldwork, and specifically a woman, could identify a mechanism that upended decades of geological consensus.
But Tharp had the data, and she maintained confidence in her plotting.
She did. But to move past that dismissal, she knew she needed independent, objective, secondary verification. And that verification came through pure serendipity via another researcher's project.
And ironically, it was a project that Heezen himself commissioned.
Right. Heezen had a colleague, Howard Faster, plot ocean earthquake epicenters, but for a completely unrelated project. He was trying to link turbidity currents to quake zones.
So he had no idea he was commissioning the very data that would prove him wrong.
None at all. That earthquake epicenter map became the invaluable secondary dataset. When Tharp got her hands on it and overlaid Foster's map of earthquake locations onto her meticulously drawn profile of the Mid-Atlantic Ridge Rift Valley.
The alignment was perfect.
It was instantaneous and just terrifyingly perfect.
The earthquakes were happening right along the axis of her proposed Rift Valley.
Not near it, not around it,
Yeah.
in it. The V-shaped valley was not just some historical feature, it was an active geological boundary. Seismicity indicates movement, fracture, energy release.
It's proof of activity.
Exactly. The fact that the world's mid-ocean earthquakes occurred precisely along the line she had drawn confirmed that this was a zone of ongoing active crustal separation. It turned an interesting geographical feature into the dynamic engine of continental drift.
So that dual evidence, the topographical structure plus the seismic proof of movement, that was the pivot point.
That was the point of no return. It forced Heezen to abandon his expanding Earth hypothesis, to accept Thup's Rift Valley, and to finally pivot to supporting plate tectonics.
And it's such a powerful demonstration of how science advances, isn't it? It wasn't just a single data stream.
No, it was the interdisciplinary connection between bathymetry and seismology that ultimately forced the consensus to shift. And it was Tharp, the person doing the tedious manual plotting in the office, who connected those dots.
So once that initial seismic breakthrough was accepted, the work had to expand immediately. Because if this mechanism was real, it couldn't be a local phenomenon. It couldn't be just in the North Atlantic.
Exactly. Tharp and her team of graduate assistants began to plot global data. They systematically demonstrated that the Rift Valley structure continued south, along the entire length of the Mid-Atlantic Ridge, right into the South Atlantic.
And then the true global implications started to emerge.
Yes, because she then found similar valley structures in the Indian Ocean, the Arabian Sea, the Red Sea, and the Gulf of Aden.
She didn't just find a mountain range. She found a continuous 40,000-mile-long global scar that wrapped around the entire planet like the seam on a baseball.
This global network solidified the paradigm shift. You could no longer dismiss the Mid-Atlantic Ridge as some localized anomaly. Tharp had physically mapped the existence of a global oceanic rift zone.
And this was the definitive, large-scale physical evidence supporting the theory that the seafloor was continuously being created and spreading outward.
It became the absolute centerpiece of the modern plate tectonics theory.
But even as she was proving the Earth's dynamic movement, her work ran headlong into a completely different kind of obstacle.
Geopolitics, the Cold War. This is one of the most fascinating and, frankly, frustrating footnotes in science history. The U.S. government forbade the publication of detailed, technically precise topographic seafloor maps.
Why? What was the specific fear there?
They feared that Soviet submarines would use the highly accurate bathymetry, the depths and shapes of trenches, ridges, and underwater canyons, for tactical purposes.
For hiding.
For hiding, for navigation, for avoiding detection. In the tense climate of the late 1950s, the U.S. Navy considered this detailed cartography a matter of national security. It was classified.
So here they are, holding the definitive proof of the most important geological theory of the century, and the government essentially classifies their data. How did they possibly get their information out into the world?
They employed a brilliant, almost artistic circumvention. They couldn't publish maps based on strict contour lines, which would provide the precise numerical data the Navy was afraid of.
So what did they do?
Tharp and Heezen decided to draw their maps in a physiographic style.
Let's take a moment to explain what that means for our listeners, because it's really key to their workaround.
Physiographic mapping treats the topography more like a landscape painting. Instead of relying purely on contour lines and numerical depths, they used shaded relief, color gradients, and an oblique perspective.
So it's like the water was drained and you're viewing the landscape from an airplane.
Exactly. This gave a powerful, immediate visual impression of the mountains, the valleys, the rifts, but it lacked the specific, measurable precision that a submarine would need for navigation.
It was a beautiful and effective act of scientific defiance.
It really was. They conveyed the vast reality of the discovery, including the Rift Valley, without providing the Soviets with the technically precise data set. They published their first physiographic map of the North Atlantic in 1957.
So they essentially converted classified scientific data into publicly accessible art.
And in doing so, they satisfied both the demands of science and the constraints of the military censors. The public could see the rift, they could understand the dynamics, but the specific navigational numbers remained obscured.
Unfortunately, while the science found its way into the public domain, the recognition for the scientists who created it was severely lacking. We have to discuss the credit disparity that followed this breakthrough.
Tharp's pivotal role was consistently overlooked in that initial wave of recognition. While Heezen and others published the major papers about plate tectonics, the papers between 1959 and 1963 that truly brought the concept into the mainstream.
Tharp's name wasn't on them.
Her name did not appear on them.
That is just staggering. The person who physically located and defined the key mechanism of the entire theory was excluded from the seminal papers that confirmed it. How could the scientific community justify that omission?
Well, at the time, drafting and cartography were widely viewed as technical support roles, not as fundamental scientific contribution.
Even though she was synthesizing and interpreting the data, not just tracing lines.
Exactly. Her immense intellectual contribution was systematically relegated to the status of mere technical assistance. The culture reserved authorship for the lead investigators and, those involved in the physical fieldwork.
And the institutional resistance at Lamont didn't stop there. The sources talk about major workplace drama that erupted in 1964 with the director Maurice Ewing.
Ewing was a powerful and often ruthless figure.
Yeah.
He and Heezen had a professional disagreement over competing theories and research focus, and Ewing cut off Heezen's access to all Lamont data.
And as a direct consequence of this falling out with Heezen,
Ewing subsequently fired Marie Tharp.
fired her. So she was thrown out of the very institution that her work had fundamentally transformed. She lost her physical office, access to the main data archives.
It was a shocking move that just showed the political volatility of high-level science. But Tharp was relentless. She didn't stop working.
She continued from home.
She did. Heezen, recognizing how irreplaceable she was, managed to continue paying her from home using contracts he secured from the Navy.
The same organization that had initially restricted her publication.
The very same. So she continued the monumental task of global mapping, but now outside the confines of the established laboratory.
And that decade of persistent, independent work eventually culminated in the visual masterpiece that introduced plate tectonics to the general public.
Yes, the collaboration with the Austrian landscape painter Heinrich Baran. Baran was a master of that physiographic technique, and together, Tharp, Heezen, and Baran realized the complete map of the entire ocean floor, merging scientific accuracy with breathtaking visual impact.
And that iconic map, The World Ocean Floor, was published by National Geographic in 1977. It finally provided a detailed, comprehensive, and beautiful visual confirmation of the dynamic nature of our planet to millions of ordinary people around the globe. It was really the crowning achievement of their partnership. Following the publication of that map, and then tragically after Heezen's death in 1977, Marie Tharp remained on the faculty at Columbia until 1983. But her engagement with maps, it didn't end with her retirement.
No, not at all. She transitioned her expertise into running a map distribution business in South Nyack, ensuring that both scientific and public audiences had access to these critical cartographic works. She never stopped being a cartographer.
And she also ensured that the raw intellectual labor of her career would be preserved for future study. In 1995, she donated her comprehensive map collection, all her notes, the detailed profiles, to the Map and Geography Division at the Library of Congress.
That donation is so key because it allows researchers today to trace her meticulous methodology. It's an intellectual goldmine. It shows how she reconciled those sparse, messy soundings into a coherent planetary map.
It cements her position not just as a discoverer, but as a methodological pioneer. Now, for many of our listeners, the delay in recognition for historical figures, especially for women in science, is probably the most frustrating part of these stories. Tharp received her major honors much, much later in life.
That's often the case, isn't it? It takes time for the impact of a paradigm shift to fully sink in. And it takes even longer for the institution to recognize the individuals who face that internal resistance.
So what were some of those awards?
Well, she received the National Geographic Society's Hubbard Medal in 1978, which was a major honor. But subsequent awards came decades later. The Society of Women Geographers Outstanding Achievement Award was in 1996. The Mary Sears Woman Pioneer in Oceanography Award was in 1999.
And the ultimate institutional reconciliation must have been the Lamont Doherty Earth Observatory Heritage Award in 2001.
Coming from the same institution that had unceremoniously fired her nearly 4 decades earlier.
A long overdue recognition.
A very long overdue recognition of her fundamental role in Lamont's legacy. But perhaps the most powerful and comprehensive honor came in 1997, when the Library of Congress recognized her as one of the 4 greatest cartographers of the 20th century.
That's incredible company.
It places her alongside giants like the model maker Irwin Reyes and the geographer Richard Eads Harrison.
What's truly encouraging is that her legacy isn't just about looking backward at past achievements. It's actively shaping the future of science.
That is the enduring influence of the Marie Tharp Fellowship, established by Lamont Doherty in 2004. This is a competitive academic visiting fellowship specifically created to support women researchers working in earth sciences at Columbia.
And it provides significant financial aid, right? Something like $30,000 for 3 months of research. It's directly enabling the next generation of women scientists to overcome the kind of institutional hurdles Tharp herself faced.
It moves beyond just symbolic recognition into tangible, career-building support.
And her recognition has also just exploded in popular science media, which shows that the next generation knows her name not as a footnote, but as a primary driver of discovery.
Oh yeah, her work is highly visible now. Google Earth, for instance, included the Marie Tharp historical map layer in 2009.
Which means anyone with a smartphone can just scroll to the middle of the Atlantic and overlay the map she drew 60 years ago. It connects the historical process directly to modern mapping technology.
She was also featured prominently in Neil deGrasse Tyson's Cosmos, a space-time odyssey in 2014. Her character was animated and voiced by Amanda Seyfried.
And that mass media feature, it really cemented her story as one of not just scientific achievement, but of overcoming bias. Tyson specifically highlighted how she overcame sexism to contribute fundamentally to her field. That shapes the public narrative about her legacy.
And the honors continue to be global and, well, celestial. In 2015, the International Astronomical Union named a moon crater, the Tharp moon crater, in her honor.
Mapping her influence onto another celestial body.
But perhaps the most satisfying piece of posthumous recognition, for me at least, connects directly back to her early professional frustrations. In 2023, the U.S. Secretary of the Navy renamed a new survey ship the USNS Marie Tharp.
From being barred from stepping foot on a Navy research vessel because she was a woman, to having a state-of-the-art Navy research vessel named after her in the 21st century.
That transformation is the ultimate validation. It's an undeniable testament to the persistence of scientific truth.
The story of Marie Tharp is so profound because she took lines of dry, technical depth data, which to anyone else might have just looked like noise or error, and through meticulous effort, geometry, and this unshakable belief in her plotting, she revealed mountains, trenches, and a continuous global tear beneath the waves.
She proved that the Earth is not a solid, static object, but a dynamic system in constant agonizing motion.
And she achieved this global, planet-defining discovery from inside a drafting room without ever having collected the raw data herself.
Her journey offers such a deep lesson, not only about persistence, but about critical thinking and scientific synergy. Her initial evidence, that bathymetric map, was rejected by consensus science.
Out of hand.
It took combining that topographical map with the complementary, separate, and quantitative evidence of global seismology to force the establishment to listen. It demonstrates the undeniable power of interdisciplinary evidence when you're challenging conventional wisdom.
Right. When you can connect two totally independent fields, geography and earthquake physics, and they align perfectly.
You have found truth.
Absolutely. The next time you look at a stylized map of the world and see that central seam running down the middle of the ocean, that mid-Atlantic ridge, remember that it was once a blank, speculative space filled in by the meticulous, persistent work of a cartographer who was told her revolutionary insight was nothing more than girl talk.
And that leads us to our final thought for you, the listener, to mull over. We discussed how Tharp's original detailed maps had to be rendered artistically, obscured from precise technical viewing, to prevent the U.S. government from classifying them.
Right. Out of fear that Soviet submarines would gain a navigational advantage, they literally hid geological truth for geopolitical reasons.
So, knowing that critical physical data was intentionally obfuscated or hidden during the Cold War due to military fears, how does that dynamic translate today?
In a world of instant global data sharing, consider what pieces of modern scientific information, perhaps related to deep-sea resources or climate trends or critical geopolitical geology, might still be intentionally hidden from public view or publication today for similar reasons of national security or competitive global advantage.
What important pieces of information might still be hidden from our view today, forcing scientists to rely on subtle circumventions just to share fundamental truths about our planet?